All right. Well, let's get into this problem I introduced today in class. The idea that I'm claiming 45% of the chips in the box are blue, um, but Rowan goes in and grabs 40 chips, only 12 are blue, which is 30%. And we're trying to decide, okay, what have we just witnessed here? Is it really the case that 45% of the chips in the box are blue, as your teacher claimed, and Rowan just happened to get an unusual or rare sample? Or maybe it's the case that there really aren't 45% blue chips in the box. And the way we can decide which of these is sort of the more plausible or reasonable explanation is we can do a thing called a test of significance and also something called a confidence interval. You have some experience with this. This, though, is brand new. So let's get into the details of the test of significance. Okay? So test of significance is very organized, very structured. There are 4 parts to a test of significance, and I'd like to kind of share them with you. The first part we call the hypotheses. Okay? It kind of revolves around the fact that there are we had these sort of 2 kind of competing explanations, and so each one of these is going to lend itself to a hypothesis. So first of all, we say we want to define the parameter, let P equal. Well, now P equals proportion of blue chips in the box. Proportion of blue chips, not in the sample, but in the box, the part we don't know, the part we're wondering what is the real proportion of blue chips in the box. So then there are 2 hypotheses that are being made. The null hypothesis, okay, we call HO, that's always going to be a statement of equality, that there's a claim is being made that the proportion of blue chips in the box is equal to a certain number. And in this case, it would be the initial claim by Mr. O'Reilly that 45% of the chips in the box are blue. And so that's what we call the null hypothesis. Now, the other hypothesis is called the alternate hypothesis. This one must sort of contradict the first one. And so there are really a couple different ways we could write this. We could say P is less than 45%, perhaps P is greater than 45%, or sometimes we just say that P is not equal to 45%. And that's what we're going to go with here, because the question really is, well, is it 45% or is it not 45%? So that's our alternate hypothesis. And then we also put in a thing called the significance level. In this case, we call it alpha is 10%. This can vary. Sometimes you have a 5% significance level, sometimes a 1% significance level, and you'll see all of them being used. Pretty much what this is saying is if the sample we get happens less than 10% of the time, we're going to start to question or challenge the null hypothesis. Now, that may not make much sense right now, but I'll come back to that in a little bit. So let's move on to the next part, which is called the conditions for inference. In order to do tests of significance or confidence intervals, you have to realize the fact, okay, we're operating on 2 assumptions. We're assuming a normal sampling distribution. And so we have to first of all decide, well, can we continue to assume we have a normal sampling distribution? And also we're using a formula for the standard error of that distribution, and we need to make sure that that formula is accurate. And so the conditions, there are 3 conditions that if they're all satisfied will allow us to assume these 2 very important pieces of the inference. So let's get into them. So the selection method, okay? Selection method. We want to make sure that our sample was randomly chosen from a binomial population. So in this case, we know that Rowan's sample was randomly selected. Remember, it says he mixed the chips in the box, and we assume he did not look in there. Rowan's sample was randomly selected from a binomial population. Now, how do we know that the population, the chips in the box, were binomial? Well, when chips were chosen, the chip was either blue or not blue. And you always want to try and write down, when you just don't say the phrase binomial population, but try to elaborate a little bit on why the population is binomial. So that's the first condition, the selection method. We want randomness and from a binomial population. So then the second issue is one of sample size. And so first we have to make sure that the sample is large enough to give us a normal sampling distribution. Keep in mind, what we have here is really kind of a binomial distribution. And not all binomial distributions will be normal. You need to have adequate sample size. And this is the NP test. So NP. So 40 chips were selected from a population. Now, we're assuming right now 45%. So that's why we want to lay out the hypotheses, because that's going to kind of establish what we're going to use for P in our calculation. So we're operating on the assumption, like, let's assume the box really is 45% blue, for now anyway. And then we'll kind of see where that leads us. So 45% times 40, I'll do the calculation here, 0.45 times 40. Okay, so 18. In other words, and that is greater than or equal to 10. So we're expecting to get about 18 blues, which is greater than 10. And then we do N1 minus P, 40 times 55. And now it would have to be the other 22 chips, which is also greater than or equal to 210. So in other words, if we sample 40 chips from a box that really is 45% blue, we would expect to get about 18 blues and 22 non-blues. And as long as those are both over 10, the sample is large enough. And so what we have here, these two pieces together, randomly selected from a binomial population, and the fact that we've met this standard, these are going to allow us to assume that we really are working with a normal sampling distribution, these two pieces together. Now there's one other size issue, and we have to make sure the sample is not too large, because if the sample is too large relative to the population, our standard error formula is going to be incorrect. So now we have the so-called 10% rule. So the sample was 40. Let me just write down the general. We want N to be less than or equal to 10% of the population. So let's check that. So we sampled 40 chips, and we're wondering if it's less than or equal to 10% of, and now there were thousands of chips in the box. And so 10% of thousands would be hundreds. And I think it's fair to say that 40 is certainly less than or equal to hundreds. And so the sample is not too big relative to the population. And because of that, that's going to allow us to safely assume that our standard error formula is accurate. So again, here are the three conditions. The randomly selected from a binomial population, the NPs, and then the 10% rule. Those are going to allow us to kind of safely assume a normal sampling distribution. And why is that important? Well, that sets the stage for the next phase, which is called the calculations phase. So now it's safe to operate under the assumption that we're working with a fairly normal sampling distribution. And because of our hypotheses, we said P is equal to, we're assuming 45% population. Well, that means we can now assume that the sampling distribution, okay, is going to be centered or have a mean of 45%. And because we've satisfied this condition right here, we can use this standard error formula to get a good estimate of the standard error. So P is 0.45. 1 minus P is 0.55. And we'll put that over 40 and square root the whole thing. Let me go ahead and do that on my calculator. 0.45 times 0.55 divided by 40. And then square root that answer. So I'm getting about 0.079, I guess, if I round it. 0.079 for the standard error. And again, I want to take 3 standard errors to the right. So 0.079 times 3 is about 0.237. So that would give me about a 0.687 at the high end, and 0.45 minus 0.237, about 0.213. So here are the percentages, okay, I would be expecting to get if I was drawing from a 45% population. Now, Rowan's sample is 30%, and I'd like to figure out where 30% is. I mean, it's certainly on the curve, but exactly where would it be? Well, now, if this is down about 7 and 14, so 30% is probably sitting right around here somewhere. So 30%, I'm estimating, is somewhere right around here. And what we're trying to assess is, okay, how unusual is this sample outcome of 30%? And the way we represent that is we're going to shade this area out here. Okay? In other words, we're like about 15% below 45. We're also going to shade this region over here, the mirror image. And this takes a while to understand, but I'll give it a try anyway. Our alternate hypothesis is saying not equal to 45. Well, that means it could be, far below 45, or it could be far above 45. So not equal to, we often call that sort of a two-tail situation. You need to kind of worry about both extremes, being a lot lower than 45 and being a lot higher than 45 if you want to differ from 45. So we're going to go ahead and shade the area to the left of 30%, but then we're also going to shade an area to the right. This would represent, okay, here's the chance that the sample is more than 15% away from the norm or the middle. So again, we call that a two-tail case. So now we're going to go through and calculate the z-score for this 30%. And the way you get a z-score is you take observe. Well, we're observing a sample of 30%. We're expecting the outcome to be 45%. And we'll put that over our standard error. And this will tell us how many deviations we are off of the middle. So 0.30 minus 0.45. And then divide that by 0.079. So I'm getting a z-score of about negative 1.898, negative 1.8. Oh, that should be 899 actually if I round it. So almost about a 1.90 standard deviation, a z-score. So I'm just shy of the 2 mark, just shy of that. So really this should probably be, just a little to the left of the second deviation, just a little bit more to the right of the second deviation. So that'd be a little better drawing. Well, now we want to figure out how much area is this. This is what we call the p-value. P-value. Of course, you could look this up on a z-chart. You'd have to look up this area, and then you'd have to multiply it by 2. And a much easier way to do this is to use your calculator. So let's see if we can kind of go into, let's see, second distribution. We have normal CDF. Okay, so this, unfortunately, this will only give you one tail. So kind of show you a few options on here. What we could do is we can take the lower value, which is just some big number. Let's have the upper value be, and we'll use the 30% figure, 0.30. And that's assuming a norm of 0.45. And then a standard error of 0.079. And so if I do that, this will tell me that, that this area here to the left is about 0.0288, I guess if I was to round it, about 0.0288. Now, of course, I could also use the z-score, second distribution, normal CDF, and then I'll use a z-score. This was a negative 1.899, but that's assuming a standardized norm of 0 and a standardized error of 1. And so again, about 0.02, yeah, still 88, 0.0288. So let me write that one down. That's this little region right here, 0.0288. That would represent about 2.88% of the entire distribution. Now, what you'll end up having to do is you say, well, now wait a minute, if this is 0.0288, then this is also 0.0288, meaning that altogether, if I took that 0.0288, multiplied it by 2, so let's try that, 0.0288 times 2, we get about 0.0576. And that's what we call the p-value. And what this represents is, it says, well, assuming the box really is 45% blue, what are the chances of getting a sample that's only 30%, or perhaps something even more extreme, meaning that, you know, even farther away than 45? As far away as this is, getting this kind of sample, or one that's even more different than 45. Okay, so once again, this would be saying about, okay, well, assuming the box is 45% blue, there's about a 5.76% chance that we're going to get a sample like 30%, or perhaps something even more extreme than 30%. And that's called the p-value. Okay, so now we're through the third phase, and we now move on to we call the conclusions phase. And so now the conclusions are where we really just use the p-value to make a decision about, you know, which of the two explanations we're gonna go with. So the first is a statement about how strong is the evidence against HO. This whole argument is pretty much we're saying, let's assume HO is true unless we build up enough evidence to try and reject that argument. So this sample provides, and so now our p-value, let's remember our p-value was 0.0576. So I look on this table right here, and this will kind of help me categorize, that's what we call the strength of evidence. So 0.0576 is in this window right here. My p-value is between 5 and 10%. And so that means I have what's called some, this sample provides some evidence against HO. Okay? It's kind of like when you go to court. Do you have enough evidence to even take this to court? And this is kind of categorizing this how strong the evidence is. How good a case do you have against HO? Well, we've got some evidence against HO. And so now we get to the next part. We're actually going to decide, okay, well, but is this enough evidence to actually reject HO? And so what we're looking for is we go back to our significance level of 10%. What this means is, okay, if we find evidence, if we find a sample that happens less than 10% of the time, we're going to call HO into question. In other words, 10% means that's sort of the level of, like, how rare does the sample need to be, okay, in order for us to reject the null hypothesis. So if we ended up with a sample that happens less than 10% of the time, we're going to reject the HO and we're going to go with the alternate hypothesis. So in this case, the question is, are we under 10% or not? Well, let's see. We found a p-value of 0.576. So we would say since 0.576 is less than the alpha of 10%, we will reject HO. Now, had our p-value been higher than alpha, we would not reject HO. Okay? We would continue to accept HO as being the truth. So again, when we're under alpha, we're going to reject the HO. If we're over the alpha, we say we fail to reject HO. So now we put it into context. Okay, what does it mean if we are going to reject HO? Well, HO said that there really are 45% blue chips in the box, and Rohan just happened to grab an unusual or a rare sample. We're rejecting that, and so now we go with the alternate hypothesis, which is, well then, what you're saying is the proportion of blue chips in the box is not 45%. And so we write words to that effect. In other words, proportion or percentage of blue chips in the box is not 45%. And again, you could probably write it in other ways. You could, in other words, we don't believe there are 45% chips in the box. We believe the percentage is something different than 45%. Okay? But make sure you kind of characterize, when you say proportion, be very specific. Talk about your population. Okay? In other words, the proportion of blue chips in the box is not 45%. So now you move on to the last phase, which is called the confidence interval. And think about this. You've pretty much just dismissed 45% as being plausible. And so the question is, well, okay, if you don't think 45% is plausible, what should be plausible? And that's where the confidence interval comes in. The confidence interval is you're going to replace 45% with something else. And so here's kind of a recap of how to do a confidence interval. Here's the structure. Here are the various Z stars that you use when constructing a confidence interval. So I went through and did all the calculations. And over here then is the interpretation. One can be 90% confident, that between 18.1 and 41.9% of the chips in the box are blue. And so those kind of go together. You kind of said, well, it's not 45, and then the response is, well, what should it be? I think it should be somewhere between 18 and 41.9. And so notice these are very consistent, saying not 45 and replacing it with this kind of range right in here. Now, I will caution you, sometimes the conclusion you get up here is not consistent with the interval you make down here, but we'll run into that in due time. So hopefully this gives you an idea of how the flow works for a test of significance and a confidence interval.